Good morning, everyone. Welcome to Introduction to Electronics and Communication subject. Myself, Darshan B, Assistant Professor, Department of ECE, SJBIT. So today we are going to discuss some topics from Module 1 on Introduction to Electronics and Communication. So these are some Module 1 contents. So in the Module 1, we are going to split into two parts, power supply and amplifiers. Consider bridge wave rectifier. The bridge wave rectifier, so we can consider the 4 diodes. Okay, so this is also a one type of full wave rectifier. So in this the circuit design, we are considering a transformer, 4 diodes formed in a bridge format, and the load resistor. Here we can consider that in the positive off cycle, so diode D1 and D3 will conduct, so that the current will flow like this from positive to negative side. Okay, during the positive off cycle, diode D1 and D3 will conduct. So during the negative off cycle, D2 and D4 will conduct. This path can consider D2 and D4 will conduct. See, here we are not going to use any center tap transformer. That is the main difference in the 2 diode center tap transformer and the bridge wave rectifier. We are going to eliminate the center tap transformer and we are going to add 2 more diodes. So in the positive off cycle, diode D1 and D3 will conduct, so the input will appear at the output side. In the negative off cycle, diode D2 and D4 will conduct, so that you are going to get the output. You can see the waveform. So in the supply voltage, for that we are going to get load voltage and load current. So in that load voltage, we are considering the maximum voltage is Vm and DC voltage is VDC. In the current, the maximum current is Im and DC current is IDC. So we need to derive that voltages, AC voltages and DC voltages is nothing but IDC and VDC. Similar way, for the AC current and voltage are RMS voltage and current, you can call it as VRMS and IRMS. Then we need to find out the efficiency of the bridge wave rectifier. Efficiency of the bridge wave rectifier is also 81%, so compared to that full wave rectifier. Then the ripple factor is 0.48. So you need to find out. Finding out the average or DC currents, we can call it as IDC. Average or DC voltage, we can call it as VDC. Consider the sine wave, so we can consider the supply voltage, we can represent Vm sin omega t. Vm indicates the voltage, maximum voltage. Consider that the cut-in voltage of the diodes are 0. So you can consider we are using the ideal diodes, and Rf is the forward resistance of each diode. So we are going to consider the forward resistance. The peak current is Im is Vm divided by Rf plus RL. We can consider, so I is equal to V by R. so that they are considering the maximum current is the maximum voltage divided by the total resistance in the circuit. Total resistance is load resistor plus the forward resistance. Then we are going to find out the DC value of load current IL. We can find out that IL is, you can write it as IL sin or Im sin omega t. So you can consider the equation IDC is 1 by pi 0 to pi IL d omega t when you are going to find the DC current. So Y means we are going to consider only the off cycle. Okay, so we can substitute that IL value is Im sin omega t. So we can integrate that sin omega t, so it becomes the cos omega t. So 2 Im by pi you are going to get. IDC is 2 Im by pi. Consider a capacitor filter. The filter circuit removes the AC component present in the DC output of a rectifier. AC component present in the DC output is as a ripple. So we need to remove that ripple. That's why we are going to use the capacitor filter. So in that, we are going to connect the capacitor across the load resistor. So consider a circuit. So you are having normal rectifier circuit. For that rectifier circuit, so you are having the load resistance. So you are going to connect the capacitor across the load resistance so that the AC component present in the DC output will be removed. How means the capacitor will store this DC and it allows the AC, so that in the output whichever the AC component is there, so that will go, so only the DC component will store in the capacitor. Suppose consider the waveform, so that you can observe in the off wave rectifier. So in the positive half cycle diode will conduct, in the negative half cycle diode won't conduct, so that the negative half cycle the output is 0. So when you are going to consider the capacitor filter, capacitor charged to the maximum value once it is in the forward bias, then in the negative half cycle the output is 0, so that the capacitor starts discharging till it gets the next voltage, so that too in the next cycle. Again the capacitor will charge and again it will reach it to the maximum value. Once the voltage is decreasing, the capacitor start discharging that. Here we can observe that, so we are going to get almost that straight line that. Okay, rectifier converts AC to pulsating DC, then filter circuit converts pulsating DC to the DC volt. So consider a capacitor filter when a voltage across the output of the rectifier is greater than V0 is equal to Vc, means V0 voltage is equal to the capacitor voltage, then the capacitor charges from a time duration of t1. So you can observe it in the waveform. This is the charging point. This we can consider as t1. When the output voltage across the output of the rectifier is less than V0 is equal to Vc, means the voltage across the output of the rectifier is less than V0 by Vc, V0 is equal to Vc, the capacitor discharges through the load resistor R1, so that we can consider, so the discharging path is the T2. So this from this point to this point, this is the discharging path that you can consider as, and you can denote it as T2. So T is equal to T1 plus T2. So this wave you can consider in the dotted line. This is thermal rectifier output. So the darkened line indicates that it is the capacitor output. That you can see that ripple. The ripple is reduced. Okay, with the capacitor filter, the ripple factor can be given by, so R is 1 by 2 root 3, F is the frequency, RL into C. So whichever the value you are going to consider, RL, that is load resistor, and the capacitor value. When you are having the more capacitor value, so that ripple will be reduced. This is for half wave rectifier. For the full wave rectifier, 1 by 4 root 3 F RL into C for the full wave rectifier. The output DC voltage VDC is Vm minus 1 by 2 of V. This is the ripple voltage, so that we are going to consider. Mainly we are going to consider the ripple we are going to remove in the capacitor filter. Rectifier converts AC to pulsating DC, and filter circuit converts pulsating DC to the DC, then direct current. So consider half wave rectifier with the capacitor filter. In that we are considering the half wave rectifier circuit. For that we need to connect the capacitor across the load. When D1 conducts, when the positive half cycle, diode D1 will conduct, and the capacitor C gets charged till Vm. You can consider this Vm. When D is not non-conducting, means in the negative half cycle, diode D is reverse bias, so that it is open circuit. The capacitor charge discharge through load resistor. So it will discharge through load resistor. So it can indicate it in the dotted line, so that we can observe that. So it will be charged and it's going to discharge. The point at which diode start to conduct is called cut-in point, this point. So then the point at which it stops conducting is called cut-out point. So the forward bias means cut-in point will come, reverse bias means cut-out point will come. Advantages of C filter. First one is low cost, small size, and good characteristics. Second point is it is preferred for small load currents up to 50 milliampere we can consider. Next, third point is it is commonly used in transistor radio, batteries, eliminator, etc. So overall, the advantage of C filter is, we can say that, so we can afford, we can use for filtering out. So consider the full wave rectifier with filter. In the, so as we are used the capacitor in the half wave rectifier with filter, same as it is, we need to connect the capacitor across the load. So consider the full wave rectifier with filter circuit. So we are having the transformer, so the 2-8 center tap transformer. We are having two diodes, so D1 and D2. So diode D1 will conduct in forward bias and D2 will conduct in reverse bias, so that you are going to get the output in the both cycle. When you are going to connect the capacitor to the across the load, so you can observe the waveform. So this is dotted line indicates that is the output of the rectifier. This is the output of the rectifier, this part, and this portion is the output of or output voltage with C. Output voltage without C and output voltage with C. So you can observe. So consider the maximum voltage Vm. The capacitor starts charging. So once it's equal to the capacitor voltage is equal to the output voltage. then the capacitors start charging. So once the output voltage reaches to maximum voltage Vm, then when the voltage is increases, means when the voltage is decreases, the capacitor is start discharging till the output voltage is equal to Vc. That so again it's going to charge to maximum value Vm, then it's going to discharge. So it happens the charging time you are going to consider as Tc and discharge time is Td. You can take time is T by 2. Similar way, consider bridge full wave rectifier with capacitor filter. Here we need to consider the bridge rectifier circuit. For the bridge rectifier circuit, we need to connect the capacitor across the load. So its bridge full wave rectifier is same as the full wave rectifier or center tap full wave rectifier. Here also we can consider that the dotted line indicates the output voltage without C, and this darkened line indicates that output voltage with C. Here also, so diode D1 and D3 will conduct in forward bias, and so means D1 and D2, and D3 and D4 will conduct in reverse bias. Here also in the positive half cycle, once the output voltage is equal to the output voltage V0 is equal to the capacitor voltage, so that point the capacitor starts charging to maximum value. Once the output voltage is less than the Vm, so that the capacitor starts discharging to the next cycle value, then again the capacitor will charge and discharge. You can consider the charging time is Tc and discharging time is Td. Total time is T is equal to T1 plus T2. So we can consider that the capacitor charging and discharging waveforms. So in this slide we are going to discuss compare Zener diode and PN junction diode. We know that the PN junction diode and Zener diode. So we need to differentiate. So PN junction diode will conduct in forward bias, but Zener diode will conduct in reverse bias. So in the first the column we consider a Zener diode, second column consider the PN junction diode. Zener diode operates in reverse breakdown condition, but PN junction diode operates in forward bias condition and never operated in reverse bias condition. Second point, so it indicates that the characteristics lies in the third quadrant, because so it's conduct in the reverse bias condition. This is first quadrant, the second quadrant, third quadrant. But in PN junction, the operation will lies in the first quadrant itself. So positive voltage, positive current. Third point is, so dynamic Zener resistance is very small in reverse breakdown condition. But in the PN junction diode resistance in reverse bias condition is very high. That's why so it will not conduct in reverse bias. Fourth point, Zener diode symbol. So you can observe Zener diode symbol, and also you can observe the current flow, that too from the opposite direction. PN junction diode symbol, you can observe the diode symbol. The current is you can consider as ID. In the Zener diode, the current you can consider as IZ. Fifth point, conduction in Zener is opposite that of the arrow in symbol as operated in the breakdown region, but in the PN junction diode, conduction in PN junction diode is same as direction as that the arrow in the symbol when forward biased. So next, sixth point, power dissipation capability is very high. Then PN junction, the power dissipation capability is very low, means we can give more voltage to Zener, so we cannot give more voltage to the PN junction diode. So Zener diode, Xenon diode will available many voltage ranges. You can consider 3 volts, 5.6 volts, 8 volts, 11 volts. But PN junction diode will be available at only 0.7 volts, because we know that in PN junction, so diode cutoff voltage is 0.7 for silicon diode and 0.3 for germanium. Next point is at the Zener diode. Application of Zener diode are voltage regulator, the protection circuit, and voltage limiters. Consider a PN junction diode. Applications of PN junction diode are rectifiers, voltage multipliers, clippers, clampers, and many electronic devices. As we are discussed that the half wave rectifier, full wave rectifier, bridge rectifier, with filters and without filters. So consider some advantages of full wave rectifier is, you know that the half wave rectifier having only the 40% efficiency there. But full wave rectifier, the center tap full wave rectifier and bridge rectifier both having 81% efficiency. So in that way, consider the advantages of full wave rectifier is low ripple. Consider as a ripple factor is 0.48. You can consider 48% or 0.48. Efficiency is high. You can consider 81.2%. So it requires only 2 diodes. For the full wave rectifiers requires only 2 diodes. This is the center tap full wave rectifier. When it comes to the full wave rectifier, bridge rectifier, here 4 diodes required. So disadvantages: it is difficult to locate the center tap on the secondary winding. The DC output is small, as each diode utilizes only one half of the transformer secondary voltage. The diodes used must have high peak inverse voltage. Thank you.